Hi everyone, in this video we're looking at the famous birthday puzzle or the famous birthday problem that asks for the smallest number of people needed in a room so that it's more likely than not that at least two of them have the same day of the year as their birthday, right? So the same problem is framed slightly differently here. I'm essentially trying to find out the minimum number of people who need to be in a room so that the probability that at least two share the same birthday is greater than 1 over 2. In both cases, I am trying to find some probability, right? Okay, the assumption is that birthdays are independent events, so no two birthdays are dependent on each other, right? So that's my first assumption. The second assumption is the uniform probability distribution, right? Uniform probability assumption, right? Which means each birthday is equally likely, right? I'm also making another additional assumption here that there are 366 days in a year. It's up to you how you want to solve this problem. Because it wasn't given, I'm assuming that it's a leap year, right? So I'm going to determine something called P of n, which is the probability that all n people have different birthdays, right? So probability that all n people in a room have different birthdays. So obviously I can get the goal of finding the probability that at least two share the same birthday by finding 1 minus p of n, right? So 1 minus p of n will determine the probability that at least two have the same birthday. Okay, so now our goal is to determine p of n somehow, right? Okay, so to compute p of n, we consider birthdays of n people in a fixed order. What that means is imagine that there is this empty room and people are entering one at a time, right? So again, that's an assumption. Empty room, people entering one at a time. And it's better to, it's easier to understand this. Okay, the first thing that happens is the probability that the birthday of the first person who enters that room that does not match with anyone else in the room. So what is the probability that the birthday of the first person entering does not match with anyone else in the room? Now, is there anybody else in the room? No. So then the probability is 1 because obviously this person enters an empty room and his or her birthday does not match with anybody else in the room, right? Now, what is the probability that the second person entering the room has a birthday that does not match with anyone else in the room, or the probability that the birthday of the second person is different from the first one? That means the second person can take any of the 365 days remaining except that one on which the first person's birthday falls, right? So except that one day, the probability of the second person not matching or probably the second person's birthday being different from the first one. Let me write it down. Second person's birthday being different from the first person or from all people already there in the room is 365 over 366. Similarly, probability of the third person's birthday being different from all those already in the room is going to be 364 out of 366. Why? Because those 2 days are already taken and we are assuming that they are 2 different days. And so the third person can take any of the 364 out of 366 days and so on, right? So now this sequence goes on and we can write that in general, for the jth person, right? That lies between 2 and 366, right? So for example, if j is 3, there are already 2 people in the room, right? So for any jth person, there are j minus 1 people already in the room, and the probability of this person's birthday being different from all those j minus 1 people in the room is going to be 366 minus j minus 1 over 366, which is nothing but 367 minus j over 366, right? So from our assumption of independence, my P of n, which I defined earlier, is going to be 1 times 365 over 366 times 364. So I'm multiplying all the probabilities because they are now independent, right? And so on up to 367 minus j over 366, right? So what is 1 minus p of n? 1 minus p of n is going to be 1 minus all of this. That's here, right? Now, my problem was asking me, to find the minimum number of people who need to be in a room so that the probability that at least 2 share the same birthday is greater than 1 over 2. So I already found, so what I found 1 minus p of n is the probability that at least 2 share the same birthdays. This is that probability, right? Oops. This 1 minus p of n, right? And I want it to be greater than 1 over 2. So essentially I have to find out my n such that or instead of j, it should be n now, right? So I was talking about n people, right? In general, this equation was for j, and now finally for n, this has to be replaced with that, right? So that I think I forgot to change. But anyways, now I'm supposed to find out what is that value of n for which this entire equation is greater than 1 over 2. One way of doing is to go and plug in the value of n and do a trial and error method. There are more sophisticated computational techniques that are available using which you can find the value of n. What I did was I plugged in different values and I found for n equals 22, 1 minus p of n comes equal to 0.475, which is slightly less than 1 over 2, which is 0.5, right? But with n equals 23, I found that 1 minus p of n was 0.506, which is somewhat what we desire, right? And so according to this, there should be at least 23 people in the room so that the probability that 2 of them have the same birthday is greater than 0.5 or 1 over 2. Okay, so this finishes our classic birthday problem. A lot of other problems can be based on this similar idea. In the next video, we'll look at something called hashing.